from OmniSci, I'm Veda Shankar. I'm a developer advocate. We have Aaron, who heads the community team, and we have Eric, also from the community team. So we'll be happy to, take your questions and learn more about your environment. Okay. What is that problem that we are solving? So as you can see, and this is a kind of probably a lot of people use this graphic. Data growth is like 40%, whereas the CPU processing power is only growing at 20%. So definitely there's a gap, and that's widening. And with GPUs, because you can pack so much more cores in a single GPU, that computational power is still growing at 1.5 times. And as you can see, the delta between the CPU performance, say somewhere like 2020, 25, you'll see that there is an order of magnitude difference between the CPU compute power versus GPU. And so that's why, I see so many hands raising, and so I think the machine learning folks are already kind of embracing CPU and GPU to do all the computation, because most of it is all matrix multiplication when you have your data set, and that is quite compute intensive. And the good thing is it is all parallel in nature, so you can definitely make use of all those cores. And also you must have heard about initiatives like Rapids from NVIDIA, where they're trying to kind of cover all the gaps in the machine learning pipeline, right? And everything is based on GPU-based data frames, right from your pre-processing to training to visualization. And OmniSci, actually we support Rapids, and we were actually one of the founding members of Go AI, which is kind of the predecessor to Rapids. And so we do support taking your data in and out of OmniSci database directly into a GPU data frame. So that way there is no bouncing back and forth to the CPU. And so it's kind of the most performant, and we'll cover a couple of slides on that also. And I have this slide because a lot of people still are not fully aware of how a GPU is different compared to the CPU. It's just the number of cores that are available. Now these are, as you can see from the graphic, even though you can do only for a particular task, a CPU is much more powerful. It can do it in 1 nanosecond, say a particular task, whereas a GPU takes 10 nanoseconds. But the fact that a typical CPU has like 20 cores, whereas a GPU has like a few thousands of cores, and you can put multiple cards. So from a single node, you could have even like 40,000 cores, and so you can get almost like 200 times more work done in the same unit of time. So that's a huge, significant difference. And also at the same time, just like how you have your computational power, you also notice that the memory bandwidth on a GPU is orders of magnitude faster than a CPU. So if you look at this graphic, you'll notice that, of course, your data lake is typically your 7.2K RPM drives. They are like hundreds or 200 megabytes per second. Then you get the SSD layers, which is your core data, 1 or 2 gigabytes per second. And then the CPU memory, when your data frame goes into CPU memory, it's like 120 gigabytes per second. But in the GPU RAM, it's almost in terabytes per second. So again, orders of magnitude faster access of data from the GPU. So OmniSci, we kind of harness both the compute, the thousands of cores that are available to us, and the memory bandwidth that is available to us. So we kind of built this database from ground up, and the good news is it's open source. our founder, Todd, he actually came up with this idea when he was in MIT, and it's an open source project, and it's one of the fastest GPU-based databases out there. And so, in addition to, so how do we make it so fast? One is with the thousands of cores that are available to us. What we do is there are analytic operations in SQL, like group by and where, so those constructs we try to parallelize it. So we vectorize those constructs so that way they can run in parallel. And because we store data in columnar fashion, not as records, when you are running these SQL statements, you're going to be actually grouping by a certain column. So we can actually store those in the GPU memory. So the way it works is you initially load the table and you're only loading those columns that are in play, and that will go from your hard drive to the CPU memory. So most of the projection happens in the CPU memory, or rather most of the selection, and then when you have to project the data, it's all happening in the GPU memory. So we take those interesting columns and load it in the GPU memory, and it stays there. So we keep the data as long as required, unless it, because most of the times you're going to be kind of using the same columns to kind of dissect it in different ways, running multiple SQL queries. Now, this also kind of, there's another technology called LLVM, which is basically a just-in-time compilation technique that we use. So what we do is we take these SQL queries and then we create query plans, and then depending on whether a query can run in GPU or in CPU, we can compile it on the fly. And we also make use of these compiled query plans because in case you are running a select statement and you're only changing some of those literals, you can actually use an existing pre-compiled query plan. And so that, again, that adds a lot of performance. So we've done so much of innovation around trying to vectorize the SQL queries. At the same time, a lot of like improvements on the compilation, smarts around how much data we can load in the CPU memory and how long it can stay. So all those things really help in speeding up the query engine. Now, at the same time, because we are GPU based, and GPUs are known for graphics rendering. Again, that's the reason why GPUs came about. Is all those pixel calculations can be done independent of each other. So all the thousands of cores are simultaneously working on rendering graphics. Now, when we run this SQL query, the data gets loaded and the results are sitting in GPU memory. So we are using the graphics pipeline in the GPU then to create the graphics rendering. So we can render millions and billions of points in milliseconds. And what we do is we then send a PNG image, which is in the order of kilobytes, to the client, so which is typically a browser. So as you will see very soon in a demo, you get the feeling that you're actually interacting with your data, even if it's a billions of rows data set. So that's the kind of a high-level architecture diagram. OmniSci platform actually consists of three components. The core, that is the SQL engine. Yeah, I have these slides. I've already sent it to Bill, so he's going to probably put it in the website. We'll also have it uploaded in the speaker deck, so you should be able to download it from there. So you have the SQL engine. and the render engine all basically sitting on the GPU, and then you have a visualization platform, we call it as Immerse, and it runs on your browser, and you can get data into OmniSci through basically by loading it through the browser. You can use like SQL commands like copy from from files or from your S3 buckets. At the same time, we also support Kafka, so you can stream insert data into the OmniSci SQL database. There are also connectors like JDBC, Thrift that you can use. At the same time, we also have a Python library called PyMapD. We'll talk about that in little detail in a while. And so you can also load your data frames into tables directly using this Python API. And at the same time, we also have JavaScript APIs. We'll also talk about that, how you can use JavaScript to kind of query the database and then use the rendering engine. So in case you don't want to use our browser-based platform, because many times you have a graphics, you already have a website, and you want to complement that data by creating your own graphic widgets. You can do that also with JavaScript. And also we have connectors to ODBC connectors, so you can actually connect to other visualization platforms or BI platforms. We have a lot of folks who use Tableau as their visualization platform, but use OmniSci as a backend because it just increases the number of amount of data that you can actually visualize and query. So demo time. And before I go to the demo, I also want to make sure I keep my thing hot. Okay. So in this particular demo, again, any questions so far? Otherwise, let me give you a quick demo just to give you an idea of a feel for what OmniSci is capable of. So, we have a number of large data sets. We have the ships demo that we were doing out here. This is a taxi, data set. It has about 1.2 billion rows and about 60 columns. So if you look at the data set, you'll notice that it's got like 1.2 billion rows and 62 columns with all kinds of information, right? And there's also another data set called New York City buildings. So these are actually New York City buildings with their polygons. So if you notice here, there's actually a multi-polygon. So this is actually the polygon structure of New York, Manhattan, buildings. So there are about a million of those polygons. So what we have done in this demo is we have actually done a join of the building ID that comes. So we know the building ID of where the taxi has picked and dropped off, and we are doing a join of that from the building data set and rendering the polygons. And at the same time, we are also coloring it, starting with blue to red on the average tip that somebody gave when they were, picked up from that location, right? So, and the thing is, as you zoom in, you can see, and now again, this is running in the cloud, but you're able to kind of, query and render like 1.2 million rows of data from the taxi data set and 1 million polygons coming from the building data set, all happening in milliseconds. And so So as we are looking at this data set, I'm going to kind of, what we have done is we can analyze many things, right? So one of the things that this particular demo showcases is the analysis of the tips that was paid during one of these taxi rides. And it's from 2009 to end of 2015. This is not Uber data, this is yellow cabs. So as you can see the tip percentage over timeline, it's been steadily rising over time from 2009, but then there's a dip every close to Christmas, so there's a nice little dip. So now if you want to you as an analyst, you want to find out, hey, why that's happening, why should I be seeing this dip in tips? Any ideas? Because I've heard some really funny ones.
I'm really tight. Prices are more expensive during Christmas.
Okay. Tourists. Blame the tourists. Okay.
The high-tech companies close during the Christmas, so those well-paid person will stay at home on vacation.
Okay. Staycation. Okay. No, good answers. But then we look at a histogram, right? Here we have the the tip percentage, all the 1.2 billion laid out in a histogram, and as you would expect, 20%, you see a nice peak there, right? So that's where the most of the distribution is. But then we also see a very large number of records which are paying no tip, right? So so keep an eye on this pie chart. This pie chart actually talks about the payment method. So, between credit card and cash. So now what I'm going to do is I'm going to just select just these zero tippers, this stingy people, right? And suddenly what happened was, if I look at my pie chart, I notice it's a lot of the number of people paying by cash has suddenly increased, right? That's now most of it is paying by cash. So let's confirm that theory. So what I'm going to do is I'm going to just go and select the cash, right? So I'm going to select all those queries which do not contain a payment method of cash. So I'm going to only select non-cash payments. And now suddenly you notice that the distribution is what you would typically expect. Most of them are 20% payers, and the tip percentage looks very steady around 20%. So what's the conclusion? So it's not that people are not paying tips, they're paying it by cash, and the cabbies are not reporting it. So, so I have faith in humanity now, restored. And
How would you prove that?
Well, there are always outliers, right?
Why they have only at the Christmas time?
I think people are, I guess, making more rides. They're probably, paying by cash, but definitely more. Most of the, the tip payers by cash, it's not being recorded. So that's why you're seeing the 0%. And also you notice the average tip percentage over here is close to 20, right? Now, also there's a heat map. Now, one of the things that you must have noticed is that as I'm clicking, everything is getting rendered, at the same time. So I'm not sure whether some of the visualization tools that you're using has this feature. We call it as cross filtering. So what you've done is you have these 62 columns, 1.2 billion rows. You have selected data, in this particular case it's tip, you could have done something else, but then you construct all kinds of charts, and then you start clicking and asking questions, and as you're doing it, the whole dashboard updates automatically. And what is really happening behind the scene, if you're curious, you could simply go and look at your developer window, right? And actually, if you go and pick, the transaction, you'll notice that actually there is something called as render Vega. So talking about Vega, that's actually an open source visualization scheme where you can actually specify a JSON, and that's how we are actually rendering the data. So the browser is basically sending a request on how it wants to render the data, what color, what size, and all that description, and then it gets rendered. Now at the same time, oops. Yeah, let me go back here. You'll also see SQL requests, coming over here.
Could you zoom in?
Sure. Let me first get this. And you'll actually, if you go back, I don't want to mess with any of my settings, but if you go and look at the network, you'll actually see SQL requests. Okay, I will probably come back to this, but basically when you break into your Chrome, you should be able to see SQL requests. So what I'm trying to drive here is, as you are clicking on these different charts, we are actually generating SQL requests, and I'm going to show in a subsequent demo how you can actually query. And the fact that we support both scalar and regular data types, as well as geo data types, you can actually construct some really fancy SQL queries combining all this data and sending it. So any questions from this demo? Yes, please go ahead.
When you were doing the cross filtering,
Uh-huh.
are those cache data, or then are you sending requests to the backend?
Very good question. So the question is, as you're doing cross filtering, are we using cache data? No, we are not caching data. But what we're doing is the fact that I'm kind of zooming in over here and all that, right? So this would automatically create a bounding box, right? So here, as I'm zooming in, what's happening? I know my latitude and longitude from the lower point, latitude, longitude, and the highest latitude. So I'm creating a bounding box. So I'm going to send a SQL query which says I need all this data of interest within this bounding box. But at the same time, what is that data that I need? I only need certain columns. In this particular case, the payment method, so or the tip, and the building IDs and things like that. So those columns for that bounding box will get loaded into the GPU memory, and it's going to stay in the GPU memory. So there is caching of the actual data, but not the results, right? So that GPU memory is going to constantly be queried against, and because it's happening in GPU, it actually happens very fast. A typical request is like in the order of 30 to 100 milliseconds. Yeah.
So does that mean that if you have a larger bounding box,
Mhm.
then your performance will suffer because you won't be able to get all of it into the GPU memory. So if you suddenly swung out to the entire United States,
Mhm.
then you would have a very large query size. Thus, would that then impact your
Yeah,
performance?
okay. So yeah, depending on how much data can be stored in the GPU memory, decides on your query response. So that's
Okay.
a good question. So, and what will happen is, if it cannot be satisfied by GPU memory, it's going to then defer it to CPU, and there are actually settings for that. Where you'll actually you can set your configuration so that way your CPU memory will then respond. Obviously now it won't be in the order of milliseconds, you might see seconds. And that kind of also tells you, okay, hey, maybe I need to add one more GPU card, or have multiple nodes. We support that too, yeah.
So one of the nice things about some other tools is that you can kind of put in comments of your thought process as you're doing some sort of visual analysis, so that if you come back a month later, you don't have to redo the analysis. So like you started here and said, hey, there's a dip, there's tips go down, and then you figured out, oh, it's because people are paying cash. Is there some way to document, add comments, or something like that?
That's actually very interesting, because I'm going to reload this, and I think Aaron here has added some comments, right? But there's not a built-in.
So we use a tool called WalkMe.
Yeah, actually.
And that allows us to sort of annotate these demos that we have on our website. But I think what you're talking about is sort of annotation of your own dashboards that you would have in the product. It's a feature we've heard a lot. We haven't actually implemented it yet, but it's on our roadmap. So if you're specifically interested in that, come talk to me afterwards, and I'll make sure that when we do get it implemented, you get first access.
And and I highly encourage it's Oh.
For this data science that you have currently, what is the amount of resources that you have in the backend, and typically what is the cost that you incur in running the
Okay, good question. Now I'm just going to keep this baby alive. Okay. Now this is running on one of our demo servers, so this probably has multiple GPU cards. Because we host the taxi data set, the ships data set, number of them, and all of them are like 10 billion rows, and this is like 1.2. So now a way to find out how much memory you need, now this would be a good way to look at your DDL, right? So here you have 1 million rows of building data. Now, and then you can look at the different data types, whether it's an int, float, if you're using like str with dictionary encoding, then you're going to definitely save space. So it's basically the data type, the number of bytes it occupies, times the number of rows. So that is all the data. But then if you look at, say, the taxi data set, that's like 1.2 billion and 62 columns. Now the question is, are all the 62 columns going to be loaded in the memory, right? So again, this is something that you need to kind of understand your data, which will help you determine whether you need 1 card, 2 cards, or how much GPU memory. But clearly, you need to have sufficient GPU memory to fit the entire data set of your query in order to kind of have that interactive, engagement. Okay. Hey, thank you. I really appreciate all those questions, and we'll be around if you have more. And also, it's very easy for you to kind of go home or to your office and try this. So OmniSci is, again, like I said, it's the core is open source. And at the same time, we have made sure that it's kind of easy to deploy in on-prem or in the cloud. So if you have, since most of you have GPU machines, you can actually download a Dockerized image, or you can go ahead and build it, from the source. Recently, one of Randy from our community team, he published how you could do that on Ubuntu. So it's fairly easy. You can just go ahead and grab the open source. Now, if you want a commercial one, you could actually get something for eval to try. Now, we also have, just like how it's easy to kind of install it using open source by compiling it or Dockerize image or just the pre-built images, both on-prem and in the cloud that you want. We could run on Azure, GCP, and Amazon. But at the same time, we also have a cloud instance. So if you go to omnisci.com, you will see a button here which says try cloud. So when you click on try cloud, it will immediately ask you for a credit card, which will be sent to me. No. Actually, it's not going to ask you for a credit card. And it's like a 14-day, your GPU, you get to have it for free. So, play with it, load your data, sanitize it, of course, don't put social security numbers and things like that. But, it's your cloud environment. And, and we in the community would be happy to engage. We have a lot of folks who have been evaluating using the cloud. And in fact, one of the rendering example that I'm going to show, I'm working with an oil and gas consulting firm. They're using the cloud. It's like 112 million rows of all the gas meters in the United States, and it's working quite well on the cloud. Yeah.
Do you standardize on one GPU architecture, or do you just have a collection of different, depending on what week you install new GPUs, is it just a different set of GPUs?
Actually, it has to support CUDA, so that's the requirement.
So it's, so it's NVIDIA.
NVIDIA. Yes.
Okay, all right.
Yeah. Okay, let's get back to the preso. I kept only for 5 minutes for that demo. That went longer. Okay, the OmniSci. So in addition to kind of loading your typical, float, ints, strings, and things like that, you also support like geospatial, objects. So this could be your point, line string, polygons, multi-polygons, and now if you think about it, I just did a hackathon with Uber, about a month back, and if you look at that Uber data set, at least the one that they shared with us for the hackathon, it was very kind of a blah, right? Picked in this, traffic zone, dropped it in this traffic zone, all numeric values, and this was the, the average time that took. But then you kind of go and, you kind of grab some other data sets which are very complementary to it. Like in this case, we grabbed the, New York City buildings. The traffic zones is something that's available publicly, right? And these are again polygons. And so suddenly there is so much of more information that you can get. What are the, the different polygons? What are the, businesses that are there? So it just, we had so much of insights into the data, which kind of looked very blah with like 5 columns. It was like 87 million records for a month. But, when you kind of marry it with other geospatial, you get a lot more information. And now with what we are seeing is more and more businesses, because your cell phone is your way of communication and all your business interaction. So your geo coordinates are invariably, part of your data set, right? So timing, so that's why we call it a spatio-temporal data, right? So we support, different forms of ingesting those data. So it could be like a S3 shapefile. Anybody from S3 over here? Okay. Anybody using geospatial stuff? Okay, a couple of hands. And so S3 shapefile is very popular. There's also GeoJSON. So these are all formats that you can simply ingest using OmniSci, using our import option. Again, both from command line as well as UI. Now, the other advantage is that there are also geospatial functions. So SQL has been extended, and Postgres has been doing this for a long time, with queries like st distance, ST intersect, ST contains. So you can construct an SQL query using these geospatial functions by taking out these columns which have the data types, right? LiDAR, anybody using LiDAR? Okay, I see one hand, very good. So we have an excellent paper. We are working with an expert, geospatial expert, who is kind of documented how you can ingest LiDAR data. Now, LiDAR is a great candidate because you're talking about billions and billions of points. These are like aerial, data points, and you can actually do a lot of analysis, like height above ground, texture of the soil, all that stuff. So I put links for the blogs that will give you more, information. And actually, talking about geospatial before we jump to custom charts, I want to quickly. I've been doing this telematics. This is going to be a blog that's going to be published very soon. You'll see it. And this is from again, publicly available telematics testing, like connected car testing is not that prevalent because everybody is so protective of their data. So I grabbed this from the US Department of Transportation before the shutdown. So, and it's got some really interesting data, in it. There's something called as onboard vehicle unit, and there is something called as a roadside unit. So there is a new form of communication, like it's the short distance, 5.9 gigahertz, communication, where the vehicle is constantly sending all its metrics to the to these roadside units, and it's used for various purposes. So if you look at the roadside unit, it has a latitude and longitude, right? These are float values typically. Now, then you have the probe vehicle data. So this is like data that is coming, that the vehicle is sending. So it's telling about its own ID, it's sending, the time, and also the mode of transmission. So the mode could be, it's trying to communicate both with the cellular as well as roadside data. So with the cellular, it is, what I found in the data set that like most of the communication is with the cellular because that's the predominant infrastructure. But as we are getting into more connected cars, you'll find more of these roadside units. It'll be used for all kinds of traffic applications. I was wondering how many of you are in telematics. We'd love to, talk and engage with you further. Anybody from dealing with connected car, testing and things like that? Nope. Okay. Are you being very secretive? Okay. Awesome.
Work on the connected car things from the IoT perspective, OBD devices, and then getting the telemetry data, and then figuring out the different analytics in terms of like the speed.
Okay, I'll definitely talk with you, and I'm going to be hanging around next 2 days also for the workshop. So, and you are the money guy from SoftBank, so we'll definitely have a chat. And so the so over here, what I did was I ingested the data into OmniSci, and the thing is, the latitude and longitude, even though they are floats, at the time of ingestion, I can ingest it as a point, a geometric point. And also, like, what I did was, basically, these are all like pandas data frame, right? Do a join with the RSU table, which has the roadside unit ID. So I can also now find out what vehicle is talking to it. Also constructed a line string, basically that represents the route. So as you can see here, most of the testing was done in and around in Virginia, like what you call as the Tyson's Corner. And these red dots over here represents the RSU, the roadside unit. And so the vehicles, as they are traversing up and down on, you'll see that visually, very simple, right? Most of the communication is happening or 300 plus 1000 with the cell tower. But if I just select only RSU, now suddenly all those other routes disappear. And I know that when they are traveling on the Leesburg Pike, that's when they are communicating with the RSU. Now, RSU is, if you think about it, is like a set-top box. It's like a Roku, just a beefed-up Roku, right? Now, if you're a traffic planner, you want to make sure that your Roku doesn't fail if all the vehicles are going to be talking to it simultaneously. So you want to spread it out. So this is actually a kind of an interesting issue that a lot of the traffic planners are doing, because they have a lot of applications lined up for these roadside units. So you can see that 89, which is somewhere over here, is actually much more busier than anybody else. So I can actually click on that and it'll tell me which one that is. Now, so in this case, I used Immerse to basically render all this charts. Now, but the beauty is the fact that now I have these data types which are geometric. Now I can actually run some interesting queries. Oops. If I can find my window. Okay, there it is. So I can go to the SQL Editor over here. And I just wanted to quickly kind of show you. So I can go to and construct a SQL query, something like this. So in case I want to find all the vehicles that were communicating with the roadside unit, what is the minimum distance when one vehicle communicated? So I want to do a select. So I use an st distance function of the OBU location, comma the communication point. I kind of cast it as geography so that I get the distance in meters. Otherwise, it'll give me in degrees, and I have no way to know how many degrees is equal to how many meters, right? And then also from the database, and also where the vehicle, the probe vehicle communication type is of type RSU. And then you group by based on the vehicle ID, the mode of transmission, and you order it by in an ascending order. So if I were to take this particular SQL, how many of you write SQL query frequently? Oh, that's good. Whoa! Okay, I should be very careful here. I'm not an expert, okay? But you can come up with some really fancy ones. So as you can see, it starts off with from 9.2 meters, 10 meters, and goes on, right? Similarly, you can do, the max distance. And you can see that now it's in descending order. So almost like 1,232 meters. Now here's a very interesting thing. So I'm going to jump to the last call over here, because what am I doing over here? Now I'm also doing, I'm trying to find out for the line string, which is the OBU path. That is the route that the vehicle has taken, but these are in small line strings. So I'm trying to see what are those line strings which are less than 500 meters from any of the RSUs when the mode of communication is RSU. But at the same time, what I'm doing is I'm going to create a table. So I'm creating a temporary table called VS temp routes using those line strings, right? So now, bingo. So, and like I said, most of these are in this case 1.7 seconds, but you're talking about, like 500,000, geometric points. And so what did we just do? We created a VS temp routes. And what I did was I put both the OBU path, which is a line string, and also the communication point, which is a point. It's a geometric point. So now I can go to the dashboard and say, hey, build me a dashboard, add chart, which is of type point map, and the data source is temp routes, and I will select the communication point, and also I'm going to add another layer to it, and I'm going to make it a line map, and I'm going to pick the OBU path, which is of type line string. And if I choose that as a color palette, and do an apply, now you can actually show your routes with the RSUs all in a single map. Okay. I know I got lost into showing you a lot of hands-on stuff, but I'm going to now quickly, because you're going to have these decks, hopefully you'll have access to. So there's also like MapD charting, where you can create your own custom apps. You don't have to necessarily use Immerse, and it's it's visualization, right? So you can create something like this. So this is something I created, and I'm not even a JavaScript guy. Just hacking around, I was able to create my own oil maps, and it's again 117 million points of all the natural gas meters, and I made a line map of all the pipelines overlaid over the gas meters, and with the time. And if I want to find out where is the Saudi Arabia of US, did you all guys know about it? The Permian Belt. So that's the future of oil in the US, and we are kind of hands down beating all the producers of oil, and kind of even on a price and in terms of volume. Okay, and then so again, there is going to be a reference blog. Look out for that, creating OmniSci custom apps for oil and gas. And PyMapD. So this is really, really important. There's a wonderful blog written by Eric, and I added a little dribble here and there. It's called Using PyMapD to Load Data to OmniSci Cloud. So since most of you are Python practitioners, you should find this super, super helpful. I wanted to actually quickly walk through it, but I think running out of time, just a couple of minutes left. So I wanted to show you that there's a huge value. Like I said, we were the founding members of Go AI. So we can talk arrow format, which is the columnar in-memory format, and from OmniSci, and Rapids also is based on arrow. So once you have data in OmniSci, you can very easily through Python code read it into a data frame that is like GPU data frame. They're calling as cuDF. It used to be called as GDF, GPU data frame. Now, so this way it is not kind of bouncing back and forth between CPU and GPU. You can have data sitting on OmniSci going into PyMap, using PyMapD into a GPU data frame, and then pass it on to H2O or XGBoost. You'll find examples in this GitHub repo, There are a number of ways to get started, like open source, community, OmniSci cloud, and of course the enterprise. So thank you everybody. We'll be outside, so if you have any questions. Thank you.